So hello, ladies and gentlemen, and welcome to our presentation about predicting bearing fatigue with eddy current testing. We would like to detect stress due to overration, and we are predicting remaining service life. So who are we? This is Dominik Stefan and myself, Stefan Sommer, and we are both in the Technical University in Schweinfurt, and our main part is bearings. Let's quickly go through the agenda. What is fatigue? What is a damage? What's happening under the surface? Then what is eddy current? How does it work? What is our reference data? Then the results, of course, and the comparison with the X-ray measurements and the eddy current measurements. Then we are predicting a remaining service life, and last but not least, a summary. Now this is me, and I start the first part. Fatigue versus damage. So what is fatigue? Fatigue is not a damage, and fatigue is not visible from the outside. So here is a cross section, and this here is the surface. And we see under the surface this half moon here, this shape. This is the dark etching region, and this is the fatigue that you can see under the surface, but only after you cut the ring. This is only measurable with destructive X-ray diffraction. Now, the surface damage, this is visible. Spalling cracks, indentations, you know it all. Here, yeah, the spalling. There is also damage in the surface that is invisible, for example, micro cracks or grinding burn, more. But this is already measurable by eddy current testing. So this is the known eddy current testing. You can measure it with the known eddy current testing. So the conclusion is of this slide, fatigue can only be measured by destructive methods at the moment, but we need a non-destructive solution. So what's happening under the surface? You see an inner ring of a bearing, a ball bearing, and the ball. And in the contact area here, you see this under the surface, this dark etching region. This is this region here. And if we zoom in, this is the surface. This is then the unaffected part of the surface. And here starts the dark etching region. And in this dark etching region, there are wide etching bands, high angle bands and low angle bands. So not to mix up with wide etching cracks. Yeah, this is a complete different story. This is not a damage, it's fatigue. So that's the conclusion. Yeah? Fatigue is not a damage. Fatigue are microstructural changes in the material, and we can measure it with subsurface eddy current testing in contrast to the well-known surface eddy current testing. And now, how does eddy current testing work? In theory and in practice. So here is the probe, and the probe is producing a magnetic field, the blue lines. So this is the probe in practice, and these are the blue lines of the magnetic field. And this is inducing eddy current into the material, those red circles here. And these are the red circles here. This is the eddy current that is induced into the surface or into the ring, to the material of the inner ring. So the conclusion here on this slide is eddy current testing is a known technology for non-destructive testing of the surface and shortly below the surface. But now, eddy current testing also allows non-destructive evaluation of subsurface material changes. Now, how do our samples look like? We are using ball bearings 6309 out of a gearbox application. We have new bearings here, 45 millimeter in bore, 100 millimeter in outer diameter. And the bearings are a standard bearing steel 100 chrome 6. smart and acidic hard heat treatment, and it's around 61 Rockwell hardness. And the used bearings are out of a gearbox that were oil lubricated, and they do not have any damages. So what we do, we cut out a section here, and in this section of the ring, we are measuring right in the middle of the contact area of the balls. We measure the X-ray diffraction. This is this hole here, right in the middle of the contact area in rolling direction. So conclusion is, this is our reference data. Now, how does this reference data look like? You see here residual stress in the raceway, and you see here the full width at half maximum. So the blue line shows the new samples. So this is a typical residual stress for standard steel and modern acidic heat treatment, the new bearings. And here the orange line, this orange line here, these are the operated samples. And this is a typical compressive stress that is typical for high load, but good lubrication. So conclusion is, the structural changes in the material has the maximum at around 0.3 millimeter in depth. This is here. And this is the reference data for further eddy current testing. So now let me quickly sum up and give you an interim summary. Today, we still need destructive X-ray diffraction testing to analyze rolling contact fatigue. So this is expensive and time-consuming. Eddy current testing is well known, but mostly limited to damages on the surface and surface near areas. We expand the eddy current testing method to the subsurface region to detect fatigue due to rolling contact. So we use new and operated samples of ball bearings out of a standard bearing steel with standard modern acidic heat treatment. And now I hand over to my colleague, Dominik Stephan. Dominik, please go ahead.
Thank you, Professor Sommer. I will now continue with the experimental results and the comparison between eddy current testing and the destructive reference measurements. This slide shows the eddy current signal measured with low test frequencies in a special sensor setup. The operation samples shows a clear higher eddy current signal level compared with the new reference samples. The new reference samples remain close together, which indicates that the reference condition is reproducible. The strongest difference appears in the subsurface region, around 0.3 millimeters. This is important because this depth range is also relevant for rolling contact fatigue and is supported by the destructive X-ray reference measurements. So the key message of this slide is, eddy current detects a clear signal in the depth range up to 0.5 millimeters, where X-ray indicates material changes. After looking at the eddy current signal alone, the next step is to compare it with the destructive X-ray reference data. This slide summarizes the comparison between the eddy current signal and the X-ray residual stress data. On the top, we see the ECT response. On the bottom, we see the residual stress profile measured by X-ray. Both methods show the most relevant changes in the subsurface region. The ECT signal difference occurs near the same depth range around 0.3 millimeters, where the X-ray data shows a change in residual stress. This does not mean that eddy current directly measures residual stress, but shows that eddy current responds to the material state in the fatigue-relevant subsurface region. The next comparison is between ECT and the full width at half maximum. For simplicity, I will refer to the full width at half maximum as FWHM. Here, we compare the ECT signal with the HWHM measurement. The HWHM values shows a clear difference between the operated sample and the reference condition around 0.3 millimeters. In the same depth range where the ECT signal shows a pronounced delta. This is the key point. ECT does not directly measure FWHM, but it reflects the same fatigue-related material state. Therefore, the ECT delta can be interpreted as a first non-destructive indicator for these subsurface material changes. Now we move from measurement comparison to concept of fatigue assessment. The Fatigue Damage Index, or FDI, is a microstructural damage indication for hardened bearing steel. It is based on the ratio between the current measurement FWHM value and the original FWHM value before fatigue. In the unloaded condition, the FDI is close to 1. Under fatigue loading, the FWHM decreases, and therefore the FDI also decreases. The important point is that the critical FDI value depends on the failure mode. For surface-related fatigue, the critical failure is around 0.86. For subsurface fatigue, it is lower, around 0.64. So the FDI gives us a way to translate microstructural fatigue damage into a measurable material state parameter. Here, we use the FWHM value to calculate the relative fatigue damage index. The evaluation is performed at 0.3 mm below the raceway. This is the critical depth range because it is close to the maximum subsurface stress and because both ECT and FWHM shows clear changes there. The operated sample has a value of about 5.2 degrees. The new reference condition has a value of about 6.7 degrees. This gives an FDI relative of approximately 0.78. Since this value is still above the critical subsurface FDI value of 0.64, the sample is not yet at a critical state. This indicates a remaining service life margin. This means that FWHM from X-ray provides the destructive fatigue reference. The next slide closes the loop between the destructive HWHM-based FDI evaluation and the non-destructive eddy current testing. We define the ETC delta as a voltage difference between the operated sample and the new reference condition. At a relevant depth of about 0.3 mm, the ECT delta is approximately 1.3 volts. At the same depth, the FDI evaluation gives an FDI relative of approximately 0.78. In our setup, this corresponds to a remaining FDI margin of about 39%, which we used here as an estimate for the remaining service life margin. If the ETC delta increases to approximately 2.1 volts, the FDI relative would reach a critical value of 0.64. In this interpretation, the remaining FDI margin reaches 0%, which corresponds to the end-of-life condition. The important conclusion is increasing ECT delta voltage indicates increasing fatigue progress and decreasing FDI. In our setup, with this material, sensor, and measurement settings, we see a roughly linear correlation. After presenting our own results, the next line compares the trend with recent international research. This slide compares our results with the results from NSK. NSK tested different materials and heat treatments. Even so, the measurement setup and ECT equipment are different from ours. The general trend is comparable. The main observation is more fatigue leads to a higher ECT voltage signal. This allows absolute voltage values are different because the equipment settings, sensor, and specimens are different. Therefore, the comparison should not be understood as a direct calibration. However, it supports the general trend that eddy current testing is sensitive to fatigue-related material changes in rolling bearings. Now, I want to translate the method into a possible application scenario. Next slide shows how old and new ECT technology could be combined in one inspection process. The first step is surface scanning with high frequencies ECT. This is already a widely used and well-known technology. It is suitable for surface near defects, such as spalling, cracks, or grinding burns. The second step is subsurface scanning with lower frequencies and a depth-related sensor setup. This new ECT approach aims to detect fatigue below the raceway, where no visible subsurface damage may be present. A precondition is that the object must be free of residual magnetism, because residual magnetism can influence the ECT signal. The key message is surface and subsurface ECT scanning can be combined in one process, for example, in bearing refurbishment. And now we can see how a scan like this is performed. To summarize, the new development is that eddy current testing can detect subsurface material changes before visible damages occurs. As in every ECT application, the method must be calibrated. For subsurface ETC, this requires new unloaded samples and used fatigue-affected samples. Ideally, these are completely bearing samples with destructive X-ray reference data. A simplified approach is to evaluate the difference between an unloaded and fatigue-affected part of the raceway. The non-fatigue damage index, derived from FWHM, can be extended towards the prediction of remaining service life. In combination with ECT, this proves the basics for a non-destructive estimation of a remaining service life. The results also indicate that subsurface ECT is not only limited to standard martensitic bearing steel. Comparable trends are also visible for other steels and different heat treatments, such as carbonizing. Finally, subsurface ECT together with common known surface ECT is ready for industrial use, for example in bearing refurbishment. Then thank you for your attention.
Yes, thank you for your attention. And we have also an AI bearing engineer in our program, and we will shortly come up to you with that AI bearing engineer with a video too. And last but not least, here are the sources we used, just for your information. Thank you very much for your attention, and goodbye.